This is Mr. Beck Does Your Homework. We're doing questions 10 and 11. Question 10 says, first, ignore any vertical motion of the lump of clay for parts 1 and 2. So we're not going to worry about that. A thin, uniform, cylindrical turntable of radius 2.7 meters and mass 27 kilograms rotates in a horizontal plane with an initial angular speed of 9.8 radians per second. It might help to draw a quick picture of that. Here is my turntable. It's rotating around an axis. It's got an initial angular velocity. And I am given the mass and the radius of that turntable. All right, the bearing is frictionless. A clump of clay of mass 9.4 kilograms is dropped onto the turntable and sticks at a point 1.7 meters from the point of rotation. So I've got a 2.7 meter turntable, and the clay is going to fall and stick somewhere like there. So here's the clay. It's going to fall down, and it's going to stick onto the turntable. Now, what I should expect is now that more mass is spinning, it should spin slower. But what I know is that my angular momentum before is going to equal my angular momentum afterwards. Beforehand, all I have spinning is the turntable. Afterwards, I've got a new angular momentum. It's going to be the turntable and the clay. So they're both spinning. So what I could do is figure out my moment of inertia for both and then multiply it by my omega in order to get my angular momentum. So since L is going to be, just like P equals mv, L is going to be my I omega, so that's to begin with, is going to equal an I omega plus an I omega for the turntable and for the mass. But they're both going to have the same omega, so I can actually add the I's together. So first for the turntable, since it is a disk, I know that the moment of inertia of a disk is going to be 1/2 mr squared times omega is going to equal the sum of the moments of inertia, so that's going to be 1/2 mr squared for the disk plus mr squared for the single mass. That lump of clay is going to be a point mass, and we're going to call it mr squared. So we get the 1/2. The 1/2 comes out of the mass being distributed from the outside to the center. When the mass is all the way on the outside, then it's going to be mr squared. Now also be careful that this r and this r are going to be different r's. The first r is the radius of the turntable itself as a whole. This r is where the disk is, where the clay is only 1.7 meters out, so that's going to be there. And then I'm going to have my final angular velocity. There should be nothing else tricky about this problem for you. So let's move on to number 11, because in this problem you're solving just for this omega. The masses don't cancel out, by the way, because they're different masses, and this is a half of this one, so you can't just pull them out. And this is just the mass of the disk. So be careful with your masses, be careful with your radiuses, and you can solve for omega. Now we get a little trickier problem, and it says calculate the loss of energy to thermal energy. Well, that's strange. How would I solve that? Well, we know that in a sticky collision, which this one is, this clay sticks to the turntable, we know that energy is not conserved. So what we're going to do is we're going to take our kinetic energy beforehand, which is all going to be rotational, and that's going to have more energy than afterwards. So I'm going to subtract my kinetic energy of rotation afterwards, and also, I'll put this in parentheses, and also my kinetic energy of the rotation of the mass that's dropped, the clay that's dropped. So this is my energy beforehand, and this is where my energy is after. I should expect this to be lost because it says calculate the loss of energy. Now, these don't really need to be separate because I could do this same thing here with with my moment of inertia. This is going to be the same. But for my kinetic energy for rotation, just like it's 1/2 mv squared, it's going to be 1/2 I omega squared. That's where it becomes different from this other one. This is just I omega. This is 1/2 of I omega squared. Just like kinetic energy and momentum are related in linear. So I've got 1/2 I omega squared for my disk alone, where this is the I, 1/2 mr squared, is going to be plugging in for that. So I'm going to have 1/2 mr squared omega squared. and then I'm going to subtract the total sum of this, so I've got all of this, but I've got 1/2 of it times omega squared instead. So what that's going to look like is minus 1/2 of 1/2 mr squared plus mr squared omega squared. Now again, be careful, because I shortcutted here. This mass is the mass of the disk. This mass is the mass of the clay. This radius is the full radius of the disk. This radius is where the clay lands. This omega is what we solved for here. And this I, of course, is being replaced by 1/2 mr squared for the disk as well. So I'm going to have a half, again, of a half of mr squared. So it's a little bit of algebra plugging it all in, but when you subtract those two, you're going to wind up with a final number, and that is going to be the lost energy. So it's starting kinetic energy minus final kinetic energy.